Baik, Assalamualaikum, selamat pagi, good morning. Welcome back. This is now practical 6, the course Introduction to Fossils at the University of Malaya. In the previous class, we looked at the phylum Mollusca, and we're still looking at this group. So this is phylum Mollusca part 2. So in the previous class, we looked at these two classes here. Class Bivalvia, where you have mollusks with two paired shells, and class Gastropoda, mollusks with a coiled shell but with no septa. Today we look at a more advanced group of mollusks, the class Cephalopoda, cephalopods. Okay. So remember, the basic body plan for all these three groups is the same. They have a muscular foot that can be specialized for different functions. So you can have them as rings of tentacles, as an organ for burrowing, or as an organ for movement on land or on the seafloor. All right. So let's look at class Cephalopoda. This includes modern day animals such as squid, cuttlefish, sotong, octopus, and also the shelled nautilus. Now, this is not an extinct organism, this is still living today. All right? So let's look at the characteristics. So the age range is from Cambrian to recent, still around today. Characteristics, they have a foot which has been modified into a ring of tentacles around a mouth. So all cephalopods have tentacles used for grasping food. And like a lot of mollusks, cephalopods have a well-developed head with really good eyes, really advanced eyes. They have good eyesight, complex eyes, and like in terms of life habit, they are marine organisms and they are nectonic, meaning that they are free swimming rather than living on the seafloor. Okay, and they move around through jet propulsion. Okay, we'll look at that later. And these cephalopods are active predators. Okay, so they can move around and they can actually hunt for food. Okay, so let's have a look a little bit on the biology of the cephalopods. Okay, so we have two cross sections here. This is a cross section of a squid. Okay, let's look at the inside. So you have the well-developed head at the front. Okay, and then you have the body at the back here, and the muscular foot has been modified into a row of tentacles. Right? So these tentacles here. So you have the mouth at the back here with a radula, a tongue-like organ with lots of small teeth on it. Okay? And you also have a beak at the front in a lot of these cephalopods. The well-developed brain and eyes. Okay? So organs at the back with gills, and also there's a siphon, just like you see in the gastropods and also the bivalves, right, for respiration. Okay. So in this case, they use the siphon to jet out water. Okay? And the siphon can move in different directions. So it is used it's used for propulsion in movement of the animal. So that's why the animal is bullet shaped here, because the movement is by propulsion, and the animal is actually swimming backwards, right? Kan dia terbalik pergerakan dia. Okay. Notice here, this squid here has an internal shell. That's the shell there. Made up of calcium carbonate, very thin, right? But it's still there. Okay. Now moving on to the next type of cephalopod here. This is nautilus. So it's a cross section now. Still the same thing. You get a row of tentacles with a beak at the back with radula. Okay. You have a well-developed eyes, gills, associated with a siphon, called a funnel or hyponome here, and the funnel can be moved at different directions, so it is used for propulsion, jet propulsion. Okay, so this animal is free swimming. So a lot of soft body parts at the back here. Now, Nautilus has a coiled shell. Okay, there's a shell here, right? And the animal lives in the frontmost chamber here. Okay, this is the body chamber, right? And the opening here is called the aperture, right? And behind it you have smaller chambers, and they can be gas or liquid filled. Okay, so these are the chambers, and the chambers are separated by walls that we call septa. So this is important now. If you look at the shape of the shell of Nautilus, it looks very similar to the shell of a gastropod, like a snail, right? It's coiled, but this is the main difference. The shell has lots of walls inside it, the septa. Okay, so that's how you differentiate between cephalopod shells and gastropod shells. Okay. So, okay, a little bit more on the shells of the cephalopods. Most present-day cephalopods only have an internal shell. This is the internal shell of a squid, a cuttlebone, right? Tulang sotong. It's made up of calcium carbonate. Except for Nautilus, which has a external shell. But if you look at the fossil record, you see that shells are external shells are actually common in extinct taxa. Okay. Most of the fossil record of cephalopods is from the shells of from the coiled shells, right? Because they are the easiest to preserve. So the shell is divided into chambers, as we mentioned before. And so these are the chambers. There's a very large chamber at the front, so a body cavity or body chamber. So take note, this is a cross section. So the shell has been cut in half. So look at it at the inside here, okay? So the body has been separated into chambers by walls that we call septa. Okay? But all the chambers are still connected together by an organic tube. So you have this tube here, and the tube is porous. And this tube is called the siphuncle. It is used to control it's used to control the fluids inside the chambers through osmosis. Okay? So those are the main parts of the cephalopod shell. So that was the internal part of the cephalopod shell if it was unaltered and you made a cross section. But how does it look like in fossils, right? So you can have cross sections of fossils if you cut the fossil into two, or there has been an eroded exposure of rock and shows a cross section of the animal. But you can also have other types of fossil preservation, like we've learned. In this case, you have a cast. You have a cast, so you don't really see the septa, right? Because the septa are inside, so you only have a look at what is outside, the external ornamentation. In this case, you have lots of ribs. So remember, these are not the septa; these are just ribs caused by growth of the shell. Okay, so that's is a coiled shell of a cephalopod. Now, sometimes you get an internal mold. The outer shell has completely dissolved. You're just left with the inner part here. So what you actually see are these lines, right? In this case, it's very intricate zigzag patterns, right? So the patterns here show the position of the septa, but they're not septa. These lines are what we call sutures. These are the lines where the edge of the septum joins the inner wall of the shell. Okay, so in the middle of the shell, the septa, then they meet the wall of the shell towards the side, so they form a line there. The boundary between the wall and the septa is called the suture. Right? And you can only see them if you have an internal mold. Okay, but if you make a cross section of this, you can see the septa. All right. So in terms of taxonomy, class Cephalopoda can be for this class. We're looking at three subclasses of class Cephalopoda: Nautiloidea, the nautiloids; Ammonoidea, the ammonoids; and the coleoids. Okay, so let's look at the three groups. First, let's look at the most primitive one. This is subclass Nautiloidea. Age range Cambrian to recent, still around today in the form of coiled nautilus. Right? The shell can be coiled, can be curved, and it can also be straight. Straight is is very common in the ancient types of nautiloids. Okay, the shell is chambered, and you have if you make a cross section, you get the septa here, and an internal mold. If you get an internal mold, you get the sutures, and the sutures are simple, straight, or curving. Right, very simple sutures. Yeah? So the pattern of the septa is still the same. So simple or curving, right? Now this is a cross section of a straight cone nautiloid. So you can see the septa here, and they're just simple and curving. And in the middle, you have this line here, and this is the siphuncle. And for nautiloids, the siphuncle is always in the middle. Okay, so we have a central siphuncle for nautiloids. So those are important characteristics for nautiloids. And like most cephalopods, they were marine, nectonic free swimming predators. All right. So just examples of photos of nautiloids in life. They probably look like this, like the nautilus with tentacles and a siphon for jet propulsion, and then you have the shell at the front. Okay. So this is again an internal mold. You can actually see the sutures, and the sutures are very simple, just straight sutures in this case. Okay. Okay. So nautiloids are very common in the fossil record, especially the straight cone autocone nautiloids, and they can actually be very big. Some of these straight cone nautiloids have been recorded to be up to 10 meters long. Okay, so this one is not really the biggest, right? So that's a childhood scale. So that is big enough, right? Quite big. So these were gigantic animals during the Paleozoic, during the heyday. Okay, so second subclass Ammonoidea. Okay, which is a younger lineage. They appeared during the Devonian and became extinct with the dinosaurs during the Cretaceous. Right, you know them from popular media as the ammonites. Right, that's one group of ammonoids. Right, superficially they look like nautilus. Okay, they have a coiled shell which is spiraling in a single plane, so they are planing spiral. Okay? But the shell is no longer smooth. They can be elaborately ornamented. Okay? Lots of spines and ribs and lots of lines and so on. Okay. How do you differ? Okay, I forgot. I forgot. Okay, so then you have sutures, the suture pattern is far more complex compared to the nautiloids, which are just simple, straight or curving, right? And now you get nice complex geometrical patterns to the sutures. And the siphuncle is no longer in the middle, but it can be in a ventral position or a dorsal position, okay, but no longer in the middle. Now, you can classify ammonoids based on the suture pattern. So it's very useful in taxonomy. Ammonoids are a very useful fossil group. They are used as index fossils to date rocks of rocks which are Mesozoic in age. They are very important there, and also Paleozoic in age. There is a very general pattern to the to the lineage. More ancient types of ammonoids have this kind of simple zigzag pattern to the sutures, gonatitic. Then with time, they become more and more complex. So they are very good age indicators. So remember that when learning about ammonoids. So you can classify ammonoids based on the suture patterns. So three orders are identified based on the suture pattern. First, you have the goniatites or the goniatitida. This is the pattern you get, or the ceratitida and the ammonitida. So we call them goniatites, ceratites, and ammonites. So the lineage becomes younger and younger and younger in this direction. Goniatites to ceratites to ammonites. Okay, we're from Paleozoic here to Triassic to Jurassic to Cretaceous. Okay, we'll go one by one to the different orders. First, you have order Goniatitida, the goniatites. So that is the coiled shell. So body chamber is here. This is an internal mold, and the pattern is of the suture is zigzag, simple zigzag pattern. Okay. And this gonatitic suture pattern is most common in Paleozoic ammonite. So by look at the patterns here, well, if you trace this pattern here, you can flatten it out on a piece of paper as a diagram like this. Okay, so this arrow shows you the direction of the aperture. This part here, direction the body chamber will be here, right? And it shows you the zigzag pattern of the suture line for gonatites. Okay, so you can use this as a fingerprint to identify different types of gonatites. Okay, different patterns, subtle differences, right? The number of the sutures and lobes, a number of the lobes and saddles here, or yeah, in the different geometries, you can give it a different name. Okay, and it is characterized. It tells you that the rocks are a different age or something like that. Okay. Okay, when you have all the ceratitida, the ceratites have a ceratitic suture pattern. Okay, you have sutures with smooth saddles and small crenulations on the lobes. Okay, remember this is direction of the aperture. So in this direction, it's aperture here. So you notice you have these smooth saddles, right? Very simple saddles curving, and then on the other side you have these lobes with smaller folds, right? Notice those? Those are crenulations. So they are pointing in opposite directions. Smooth saddles in this direction, and then pointy crenulated lobes in this direction, right? So see, crenulation smooth. So this is a seratitic suture pattern. Okay, these are younger and relative to the gonatites. Then you have the ammonites, which are the youngest lineage, right? They went extinct with the dinosaurs during the Cretaceous, okay? And they have complex sutures with secondary to higher order folds. So very complex geometric patterns. Yeah, this is more complex, right? So this is kind of pattern is called ammonitic. And these can be gigantic, up to 2 meters in diameter. They were swimming with the dinosaurs, okay? From the UK. Okay, so those are the ammonites. So you have the three orders of ammonoids, and they are very useful in dating rocks and correlating rocks. And uh, you look at the suture patterns to determine the age of the rocks. Just to show you photos, examples of ammonoids, these are from Malaysia. Okay, so this one is going in this direction. So the aperture is here, the body chamber is here. This is a very poorly preserved specimen. But you can still see the zigzag pattern of the suture line. So this is a gonatite. So the genus name in this case, it is gonatitis. Okay. So this is another ammonoid here. You can see the suture line here, much larger specimen here. Both of these are ammonoids collected from Bukit Tuntung in Pauh, Perlis. Okay, all these are from Perlis in Malaysia. Okay, and they are carboniferous in age. So this is Predara ilitis, that's the genus name, Tuntungensis. The trivial name is Tuntungensis because they were found at Bukit Tuntung in Perlis. One more photo to show you a Malaysian fossil, right? So these are ammonites. You cannot really see. You can see a little bit of the sutures here, right? But most of this is just external ornamentation, right? The sutures are inside. Okay, and these are from Sarawak, okay, near Kuching, okay, and they are from rocks of Cretaceous age. Okay, so you can actually find ammonite fossils from Cretaceous marine deposits. So if you're trying to look, if you're interested in dinosaurs or marine reptiles, one place to look for these kinds of things is the area near Kuching. You got the right type you got the right rocks of the right age there. Okay? If you find ichthyosaurs or plesiosaurs, if you can try there, okay? Or even dinosaurs. Okay, so that was subclass Ammonoidea. Now let's look at Coleoidea. Uh, so this one will be the most familiar to you. Again, a lot of the members are still around today, right? You have a soft body, and the shells are inside, or the shells are absent. For example, in octopus, there is no shell. Okay, and in cuttlefish and squid, you have an internal shell, right? But if you look at the fossil record, the most common type of colloid that is preserved are the belemnites, okay, members of the order Belemnitella. Okay. Now, superficially, they look like modern-day squids, right, with tentacles, a head, a funnel, and a soft body. And then they have an internal skeleton, but the internal shell is different from what we see. It doesn't look like a cuttlebone. Okay. Age range: these animals living from the Carboniferous up to the Eocene. Okay, and the internal shell is bullet shaped. Nampak macam peluru ni. It's bullet shaped and divided into two parts. First, you have the shell. The actual shell resembles the shell of other cephalopods. This is the phragmocone. The middle is conical. There's a siphuncle. There are septa separating the chambers. Okay, but in front of it, you have this solid bullet-shaped body of calcium carbonate that we call the guard. Okay, solid calcium carbonate. It's bullet-shaped here. So that's the guard, and because this is broken into, you can actually see the phragmocone inside. Okay, and these are belemnites. Okay, so belemnites have been reported again from Cretaceous deposits of Kuching. Right? So they were living together with the ammonites, and most likely were living with other marine reptiles such as plesiosaurs and ichthyosaurs. So try to find, if you're lucky, it'd be great. If you find any marine fossils from there, marine vertebrates. Okay, so yeah, in this cartoon I showed you. So that is how a belemnite looks. For the more and for the good scientists in the class, they start to ask, how do you know that is the shape of a belemnite? These are already extinct during the Eocene, right? And they had soft body parts. How do you know the shape? Well, we got specimens like this. Remember, sometimes in very exceptional cases, you can actually get soft parts being preserved in the fossil record. So here you have the belemnite guard and the phragmocone, the front here, right? And associated with a body with tentacles, and then you have small hooks associated with the tentacles here. It looks very similar to a squid, the just sotong. So why is this well preserved? Well, it's associated with shale, which is high in carbon, lots of organic matter inside it. Right? So it was probably an anoxic environment, low oxygen, so slow decay. There was no oxidation, so you get really exquisite preservation of the soft parts of the animal. Okay, so yeah, we know how the belemnites look because we have these kinds of fossils. Okay, so I'm going to stop here. We have a few more groups to look at. After this, we'll be looking at the echinoderms, more advanced group, and then the arthropods, and then we'll finish. We'll look at the main groups. In this class, we'll focus on invertebrates, animals without backbones. We'll just stop with arthropods and echinoderms. If you're interested in more advanced groups, take paleontology in second year, okay, or there's also advanced paleontology in third year. Okay, so that's it. Bye.